Why will you remove it? It's crazy.
Yes.
Let me know when I'm ready, alright?
Yeah, no worries. Take your time. There's no rush. I hate these two chapters anyway, so.
How vast is the non-visibility of ground from the cockpit of a quick turnaround? 17 meters. Wow. Glad that somebody wrote the answers.
Okay, you best.
Retake test. No good. Let me take a picture of this just because. So I have it as proof. Continue. But what happened here? My phone was still there. What happened?
still saying that it's there.
Why? They wanna test? They wanna study again?
Yeah.
Figured it out, Dennis?
Huh?
Did you get it?
Yeah, no. I mean, I probably got to wait a day or so.
Okay.
I'm ready whenever you are, Brandon.
Cool.
Navegación.
All right. How do we begin this? So tomorrow, it's our quiz, right? I was looking over what we got to cover tomorrow. Tomorrow's a lot like today in the sense that it's so much information for no good reason. I genuinely hate teaching navigation, autopilot, and communications, not because they're difficult, but because I feel like a lot of it does not pertain to us, right? A lot of it has to do with the displays of what caret pops up when and what graphic pops up when you engage autopilot, disengage autopilot, something we'll never see, right? And so in building this class, I try to trim it down as much as I can. So a lot of the videos, a lot of the slides we're going to see, it might seem like we're going by it really fast, but it's because I'm just going to wait till the CVT so you can actually see. So me explaining to you that at 2,000 feet, all of a sudden a little red dot comes up, it just makes no sense. There's no reason for me to tell you that, but the CVTs will. So we'll do that. I'll tell you what you really know and need to know in terms of maintenance. Autopilot, the same thing. Communications, there's nothing. I mean, the way every plane communicates is the same. You have VHF, you got HF, and that's it. And SATCOM, right? But my purpose then is to just teach you how to navigate through each one and what you can and cannot get away with. That's about it. Then lights, again, here's a light, there's a light, this is a light. It's nothing crazy. It's nothing new like, for example, the 787 or the 777 or the 350 where the lights are like smart and they tell you when they expire and there's logic to it. None of that exists here. So we'll go over it and that's it. And then we'll do the review. If we finish early today, I'll do the review today. If not, then we'll do the review tomorrow. The reason I say we'll do it today is because tomorrow the test, maybe 1 or 2 questions from communication and maybe 1 or 2 questions from light. So, and we'll go right before the test anyways. That's it. All right. So the first half of every chapter is going to be like, I'll be speaking a lot. And then it gets to a point, once you start seeing the links, it's because there's no really reason for me to be talking. So then we'll watch the CBTs and then go to lunch and then go home. Okay? Cool?
Coolio.
Sounds good. Let me shut off the light then. Alright, so navigation, right? And the main component of our navigation system is our ADARUs, right? It's not technically an ADARU because it's not the unit itself. Well, of course, there is an ADARU unit, but it's the system. So it's ADIRS, but I'm just going to keep saying ADARU for that time. In any case, you have one ADARU. It's not like before you would have multiple. There's one ADARU, and within it, you have backups. So instead of having 3 different boxes, what they have is one big ADARU in place of 3 different boxes. And then you have what is known as a SARU. So if Air Data Inertial Reference Unit is the main component, our SARU is the backup, and it stands for Secondary Attitude Air Reference Unit. Right? And basically, when the ADARU fails, this is what takes over. They're both no-goes. So if your ADARU is great, but your SARU is broken, no-go message. No dispensation. And likewise, if your ADARU is broken, then you can't just fly with your SARU. Right? So, ADARU, main component. air data and inertial reference, hence the name air data inertial reference. So it gives you both data from the static and the pitot probes, as well as the gyros within the ADARU. Okay? You have ADMs, or air data modules, one for every probe. Okay? Every single pitot probe there's 3 pitot probes, left, center, right. So you have 3 ADMs. You have 3 static ports, left, center, right. So you have 3 ADMs, each one. We have 1 total air temperature probe and 2 AOA sensors. The AOA sensors are on either side of the airplane by the nose. I'll show you a picture momentarily. And, yep, this thing's converts air. So what do the ADMs do? They get some sort of pressure signal, right? They get some sort of analog signal from the air pressure. It takes it, it converts it to ARINC 629, and then sends it to the ADARU. So its main purpose is basically a converter of data, right? You're going to get dynamic pressure here. It has to convert it because the ADARU doesn't know how to convert it, or rather, they just separated it. And then the static port, same thing, it's going to give you static pressure. Again, a SARU, or supplies pitch and roll attitudes, as secondary source to PFDs, primary flight computers, and auto flight director system. We're going to talk about that next, but in any case, the SARU, just think of it as the backup. It performs basically the same functions as the ADARU, just not to the same level. Right, so the inputs, we just said, pitot probes through our ADMs, static through our ADMs, total air temperature, and our AOA sensors. All right, and it's just showing you where everything is. So your ADARU up here in the overhead panel is where your ADARU switch is. Then you have your integrated standby flight display. So that's your backup display from your PFD and ND. Excuse me. And then you have your source selectors on the side if you want to go to an alternate source. So for example, if your ADARU data looks like it's giving you false data, you could switch over to the SARU. And then you have your CDUs on either side, one for the captain, one for the FO. Okay, we saw yesterday when we went to the MEC that the ADARU is underneath at rack E3. There's a protective cover here, so you won't be able to see it. But the other ADARU is on the other side. Nope, where is it? No, the ADARU is here. Sorry, the SARU is here. That one is visible. That's on the E2 rack. It's on the right-hand side of the airplane. We have our power supply assemblies. We saw 2 in the flight deck, rather in the main equipment center, and 1 in the E5 in the forward cargo compartment. So one of them is there. The last 2 are there. Those are the ones with the circuit breakers in front, right? And then you have your ADMs all thrown in there. So right here, this is the E3 rack, right? It's just down here. And then it's this protective cover. That protective cover is there so that when you climb up and when you're walking back and forth to your circuit breakers, your foot or your boot does not get caught up in there. That's what that's for. And I guess they figured that the AIMS cabin is okay because it's by your knees or by your waist. Right? So you got the left pitot ADM, or air data module, over here in the crawl space past the car file system. Yeah, this is not working.
Man, we're in a bad position here.
Oh yeah, that pipe breaks. Yeah, that's the sewage pipe. Yeah, that pipe breaks. It's over. Absolutely, 100%.
I was like,
Yeah.
what the hell?
Yeah. And then again, of course, up here between the MEC and the floor up above you is where the other ADMs are. Remember, you have 1 ADM for every single source of air you're getting. So again, you have left, center, and right. You have 2 per, 1 pitot, 1 static. That's a total of 6. So you have 6 ADMs. Okay. We also have, if you notice here, a pitot S ADM. That's a standby air data module, right? So we have a separate. We have 2 pitot standby air data modules, and that's for the center pitot sound, and that's going toward the SARU. We'll get to that point, but I just want to point that out there. The other remaining SADMs are in the forward cargo compartment. All right, so they're there, up in the overhead. Okay. So what's going on here? Right? So we got our Adderall. It's getting power from the 110 for the P110, from the P210, as well as the 310. So it's getting a lot of power from different sources, and that's done purposely, just as redundancy purposes, right? What else do we have here? We have our P11 panel. There is a circuit breaker that controls the ISFD, or integrated standby display. You also have a circuit breaker here that controls the SARU. They get powered independently. PFC, or primary flight computers, and Adderall powers, that is what gets its information from there too. And the PFCs get the power on the screens. It's just basically telling you that these are powered up. It needs to know that, and you'll see later on the bus interface that the Adderalls get their information from the PFCs, or the primary flight computers, in order to correct their air data. Right, so you got the Adderall. Again, left bus, right bus, hot battery bus. All just in case of one bus fails, you have 3 different sources. The left AOA sensors are getting powered from, it looks like the left, well, they both get power from both buses as well, if you can see here. Right, if P110 panel, the left bus is powering the left AOA as well as the right AOA, and likewise, this left AOA is getting powered from the right bus, and so is the right one. All right, so again, it's all done for redundancy purposes. You don't want to put all your eggs in one basket, and so therefore that is why you put them on different buses. Notice the SARU is also on a different bus, right? So we have left buses, AC and DC, right buses, AC and DC, hot battery bus. This one's on the FCDC bus. Each PSA power panel to its respective pitot and static ADMs. So for example, the left PSA powers left pitot ADM, and the right and the left static ADM. So again, if you remember what the PSA stands for, that's power supply assembly. Those are the boxes that control or supply power to the flight controls. Right? Those are the 3 ones with the circuit breakers. I'll show you a picture if you don't remember. Where do we cover that? We covered that in electricity, right? Okay. Those are these. Remember the one with all the circuit breakers that I told you? Here's the battery interlock. Make sure it before you do anything with the flight controls, so you don't drain the flight control batteries. All right. I could have sworn they had a video that showed you it. No, I know where it is. Showed you. I didn't have the video. I showed you the video. That video is here. Oh, that's not YouTube.
Grammarly can help you rate quickly and confidently, so you never have to slow down at work.
Okay, so this is the E5 panel. This is one of the power supply assemblies. The other 2 are found in MEC. Okay, so that's the power supply assembly. They supply power to the ADMs, to their respective ADM.
This is about 20 feet.
Okay, that's a little better closer view. So E5 panel, PSA or power supply assembly, they supply power not only to the flight controls, but they also supply power to our air data modules or ADMs. So if you have a left PSA, it supplies power to the left ADM of both the pitot and the static. Right supplies the right pitot, static, ADM, and so on and so forth. Right? That's all that slide is telling you. Here is our Adaru's digital interfaces, meaning where it gets its information from. So again, remember, the pitot probes each have their own ADM, so left, center, and right. And what they do, the pitot gets dynamic pressure. That pressure is then sent over to the ADM. The ADM breaks it down, converts it into an ARINC 629 signal. That signal is then sent to the Adaru. It's also sent to the SARU. And as we're going to learn later, they're also sent to each primary flight computer and to every auto flight director computer for the autopilot system. And then we'll learn about this in chapter 27 next week. This one we're going to learn about later today. But it's just letting you know that all this air data, all of it, has to be sent to the Adaru, to the SARU. This one is not a 629. It's here, but the ISFD gets its information 429. So that's the oddball one. Okay, so the integrated standby flight display is on an ARINC 429 bus. Okay, so that's the odd one. But again, if you look here, it gets all its information here. What also gets its information onto these buses, you notice, is the total air temperature, the AOA, PSEUs, and that's the proximity sensing electronic unit. It has all the information, or interprets all the data for all the near far sensors, and your flat slat electronic unit data. Again, all of that is sent because if your gear is down, or if your slats or flaps are extended, then the Adaru has to compensate for that. You have to compensate for that, and so does the primary flight computers, and so does the auto flight computers, just in case you're doing an auto line. So again, all this data, all this input is shared onto the 629 bus, and it's sent to its respective place. So if you look, the Adaru, but you also have to see that the Adaru does not speak on every control bus, okay? If we look here, the Adaru speaks on the left flight control system, or sorry, flight control ARINC 629. And it also speaks and receives data from the right, but it only receives data from the center. See that? Only one-way arrow. The SARU is what speaks to the center. And again, that's done purposely because your Adaru, you're going to want two interfaces, but if this fails, then you don't know if it failed because it wasn't receiving data. So just to be on the safe side, instead of having this get its data from the same ones, or rather speak on the same bus, it is going to speak on the center. In fact, whenever you think of SARU, I want you to think of center stuff. So the SARU speaks to the center pitot tube, center static probe, all right? So center is typically reserved for standby stuff, all right? So again, the SARU is talking on the center, but it's receiving information from all that, and that's possible. Remember I told you that you can have multiple couplers on multiple buses. Right, so those are on the 629. You got your TAT, again, your left and right AOA sensors. That's all the information being fed to the AIMS cabinets. Your flat electronic unit and proximity sensor units send landing gear data to the AIMS to calculate for corrected AOA. All right, that is why we need information from the PSEUs and the flat slat, because all that information that they gather from their respective sensors has to be sent here so that it can make calculations. And then again, like I told you, that the ISFD, or Integrated Standby Flight Display, does not receive its information from on a 629 bus. Instead, remember I told you there's a standby air data module. You don't see it here. There's a standby air data module that sends it on a 429 bus. So that's the oddball one. Whoops. Go back. All right, so the other thing, get my markers. The other thing to know, I know I keep saying that there's a left, center, and right pitot tube, but really there's two per, think of it as a system. So let's say this is the nose of the airplane. Okay. It's the radome, right? And some cockpit windows, right? So you have static, and then you have these static ports on the other side, and this is interconnected. I'll show you in a bit, Virgilio. Right, so these are interconnected. And this would be, let me see how it's labeled. Can't see it. But it's like left, center, and right. Left, center, and right, and left, center, right. Okay, so they're connected. So there's two probes, is what I'm trying to tell you. The pitos are different. The pitos you have a left, center, and a right. Left, center, right. But the pitot probe, what the static probes is what I'm trying to tell you is on both sides of the airplane. Okay? And that fourth one, you see a fourth one, that's for a cabin static. That's for something else. So we see here the bottom pitot probe, that is the left pitot probe. The one right on top of that is the ice detector. On top of that, that is your TAT or total air temperature, and there's your left AOA. Right? So that's what's on the left side. So my drawing's a little bit off because this should have been here. The center is this bottom probe right here. Right? Center pitot, ice detector, right pitot, right AOA. Okay? So there are indeed only 3 pitot tubes. And there are 3 static ports. Or I should rather say, like I wanted to say, static port systems. Because there's 3 probes, 3 here and 3 on the other side. Right? So this is what I wanted to show you, right? You have a static port on the left side, but you also have a static port on the right side. And they're interconnected. And then they're connected. Again, remember I told you the sensor goes to the standby and a static, okay? So notice that the standby air data module is only for the sensor. That's it. Again, if you look here, pitot, standby air data module, center. Okay, so the center, all of that is exclusively as a backup. So for your ISFD.
So you have 2 SADMs.
2 SADMs, because remember, every single probe has its own, right? And because, yes, and then because it's a standby, you're not going to use the same ADM. You'd have to have a backup, its own ADM to interpret. Basically, it's the backup, right? And so that's why you have 2 standby ADMs, because it's one for the pitot and one for the static. Again, and so if before I was showing you what they were talking about, still the same picture, okay? Just drawn differently, right? So again, remember, this is just letting you know on what flight control airing buses it talks to. How many flight control buses we have? 3, right? There, here they are. Left, center, right. How many system? 4. It's left, C1, C2, R1, R, right? That's system buses. Okay, so I'll just write it here again. 11 airing 629 buses. 3 flight control, right? 4 sys and 4 aims. Right? And this is just for the aims cabinets to talk to each other. Okay, but now that we got that, so here's our left, center, and right. Notice that everything talks to on side, meaning the left pitot ADM talks to the left flight control bus. If you see here, the center pitot ADM goes to the center, and the right, of course, to the right, right? So they talk on side. And again, I want to stress the point that the ADARU talks to left and right, and the SARU only talks to the center. But they all still receive information, from all 3 buses. Okay. What else is there to say? Again, that's the only thing. So if you're thinking of a pitot probe, which one is it? It's probably talking, it definitely is talking to its own bus. It has its own ADM, and it's talking to the ADARU. When we get to the center, yes, the center has its own regular ADM, talks to the center bus, but then it taps off that information and also sends it to the standby, dedicated only for the ISFD. Okay, so it gets its own source purposely, right? And then here's your static, SADM. So if the question on the test said something like, which pitot static system has more than 2 or has 2 ADMs per probe, then it would be center, because center has ADM, and SADM. Okay? So the sensor has 2 ADMs per probe. 2 for the static, and 2 for the pitot. Okay. Good. Okay. Adderall, nothing crazy. Black box, side handle. It is, though, mounted in a certain way where it locks in place. So it has what is known as a locking bar, meaning you cannot unlock it unless you take off the connectors. Okay? So, for example, see here, no connectors here, right? There's no connectors here. It's locked down. If you put your connector here, if you try to unlock it, it can't because it's going to hit the connectors. So you have to first take off all the connectors, then this handle lifts up. It's just a fail-safe, just to prevent you from, maybe this is a better picture right here. Right? This is the locking bar, so you have connectors here. And if you want to take off the Adderall, you first have to take off the plugs, and then you can pull up the locking bar, and then you can remove the Adderall. Right? That's the main takeaway here. But to say the Adderall has internal redundancy and automatically makes allowances for failures, and redundancy management selects a value from the inputs that come from more than one source. What does all that mean? All it's saying is that think of this as it's in partitions. Right? So it has about 6 gyros in it. Look, here it is. 6 gyros, 6 linear accelerometers, 4 processors, 3 power supplies, and 3 dual-channel ARINC69 input-output interfaces. Basically, you can divide it into 1 channel has 2 accelerometers, 2 laser gyros, 1 power supply. And so normally in other planes you had 3 Adderalls. Now you only have 1, but it's still 3 inside. Think of it that way if you want to. Right? In addition to, if for whatever reason, catastrophe, you fry that whole box, you shouldn't though because it's really compartmentalized. But if you did, you had the Saru. That's the locking bar. Right? And this is just showing you how that redundancy works. So, remember, you have the Adderall talks to the left and to the right, but it receives information from the center. So you have 3 different modules. Here's 1 module, 2 modules, 3 modules. You have 4 processors. 1, 2, 3, 4. Each one pertains to here, and you have a spare one. You have 6 gyros. You have 6 accelerometers, so think of it as 2 per. And 3 power supplies. Again, think of it as 1 for each. Okay? And what this takeaway, you should see from here is that depending on what kind of failure you have, the Adderall could still be operable. For example, if you have a single failure, a single module, maybe 1 accelerometer is not working, or maybe 1 power supply is not working, then you're going to get a fault, but you're still good to go. It's when you get 2 faults, right? So if you get, let's say, 1 accelerometer and a power supply, then that's called multiple failures. Or if you have 2 in the same one. So if you have 2 accelerometers, even though it's 1 module, 1 compartment, you still have 2 failures. And that's not good. All right? All right, so if a single FCM or fault containment area fails in 1 FCA, fault containment module, if 1 FCM, 1 fault containment module, fails in any fault containment area, which are these 3, then you have a single FCM failure and no more, blah, blah, blah. The Adderall sends data to the AIMS to make a maintenance memo. So this fault right here, you would see it in the CMCF, but only if you looked at your faults, right? It wouldn't be a flight deck effect. So if you had 1 failure of any part here, only a maintenance memo. Only you can see it. Right? It's when you have 2 faults in any given area or 2 in the same one is when you're going to have the Adderall status message, and that's a no-go. Okay, so if you have 2 fault containment module failures in the same area, the Adderall sends data to AIMS to make a maintenance message show on the MAT, and the status message Adderall shows on the ICUS display. Where would it send it to AIMS? What do we think? Where would it send the fault to?
CMCF?
Yes, good. CMCF. Where's the CMCF live? Which module, James? Just tell me the modules in AIMS. What do we have?
You AIMS is both.
Good.
Yeah.
But that's ACMF.
Yeah, AIMS.
Okay, that's for reports, for hard landings, over exceedances, engine exceedance, vibration. This is for faults. It's CMCF. Okay, so the CMCF reports any fault from any system. Okay, so what are the modules? We have IOMs, right? 4 IOMs,
Yes.
2 GGs,
GPS.
one, if it aims to its CPM standard, and the other one is CPM communications. The CMCF function lives in communications. Okay? So, right here where you see that AIMS, and the Adderoo is going to send the message to AIMS, it's going to send it to AIMS, but it's going to send it to the CPM COM. That's where it's going to go to. So that's where the CMCS lives. Air data module. Air data module. What do we got here? We got a few things, right? So if you look inside, you have a power supply. Remember, our power supply for the air data module is PSA, right? So power supply, that's great. Here's where we get our pressure. That pressure goes into a sensor. That sensor goes through a converter to change it over. You have a calibration and temperature compensation, so it's going to get information from the TAT to compensate for any changes in degrees or anything. And then eventually it's going to go to its 629, right? So it goes from analog to digital, gets calibrated, then it goes to the 629. Okay, great. Again, this is nothing you have to really worry about. Power supply, a processor or byte logic, so it's basically it's the brains of the operation. This is operational, OPS, it's operational, and then it says NVM or non-volatile memory. It keeps a memory or it keeps a local memory of the things it's going. Notice here though, it has a pitot probe heat. And so the ADM sends the signal to the power management units for heating of the probes. Okay, so if the question on the test adds something like, where does the probes get its heat signal from? It would be the ADM. Right? So if you're left, so there's two, we're going to learn about that also when we get to rain and ice, but for now, there's two signals you can get. You get a ground signal and an air signal for your heating, right? As long as one engine is running on the ground, you're going to have low heat, if you will, right? Some sort of heat to the probes. If you're in the air and you're going more than 80 knots, that's when you get the air, and so it boosts it up. It boosts the heat signal up. But where does it get that information from? Or where does the pitot probe get its information from? From the ADM, right? Because the ADM, you got to remember, is connected directly to the pitot probe. Okay, so part of the processor and byte logic, it's going to let you know whether to give the probe ground heat control or air heat control. Remember, ground heat control is like a lower heat temperature. You only need to have one engine running. As soon as your engine runs, your probe is going to send the signal. The air heat control is, again, like I said, the moment you get into the air and you're traveling a certain speed, or rather you're in air mode and traveling a certain speed. Okay? So the main takeaway here is that the air data module, aside from converting this pressure input, whatever the pressure, whether that be static or dynamic air from the pitot pressure, whatever it is, it senses it, it converts it, calibrates it, and then sends it onto the 629 system to go to the Adderoo and or SARU. So the ADM senses, converts, calibrates, and eventually sends to ARINC 629. Right? That's the job of the ADM. It gets an air pressure, be it static or dynamic air from the pitot or static respectively, or it's gonna and then it converts it to a digital output, calibrates it based off whatever information it's getting, and lastly sends it over to the 629 system. That's its main objective. What do we got here? What fun facts do we have here? ADM supply an air heat signal to the power management panels when any of these conditions is true. The airplane is in the air, and the computer, I should have said calculated, airspeed is more than 50 knots. I told you 80, 50 knots. I apologize for that. So if you're in the air and you're going faster than 50 knots, I don't know why you would ever be in the air and not faster than 50 knots. That doesn't make sense to me. So they should have just said the air heat control is the moment you get off or you're in the air, and the ground is when you're on the ground with one engine running. Okay? Computed, calculated, either way, it's still the airspeed that's been adjusted. That's what an ADM looks like. So if you look here, this is where it's actually connected to the static or pitot probe. So this is the line pressure, the pressure lines. All the modules that you saw in the previous graph, they're here. It's so the sensing element would be right near the probe itself. Sensing element, then it would go through some conversion element, calibration element, and then lastly it goes to the ARINC 629 bus. SARU, Secondary Attitude Air Data Reference. I didn't put unit, but it's there. It's just a black box. It's just a black box, very similar to the ADARU in the sense that it receives air data information and sends it to where it needs to. The only difference is that it doesn't have multiple channels like the ADARU does. Again, it's only for standby. So the SARU is the backup source of the attitude and air data. It is the backup. When the ADARU fails, this is what takes over. Or this, rather, is what gets the information from. The Autopilot Flight Director system uses the SARU backup navigation data if the ADARU fails. Again, we're not speaking about that yet, but we will be speaking about the auto flight system next. In any case, just understand that the SARU, aside from supplying attitude and air data, right, or inertial and air data, it also, the SARU also gives a backup navigation data. And it has cooling fins, because it's passive cooling. There's no forced cooling onto this. No MEL relief, so no forts or no dispatch. Again, the SARU is a no-go item. Must be working. Because it supplies all its information, not only is it a backup, but remember, it supplies all its information to the integrated standby flight display, and that also is a no-go. Right, so this is what it looks like. It's pretty big, to be honest. And this is what it looks like down in the E2 rack. So on the right side of the, and we see it, and here's the other power supply. Here's another power supply. So it's right next to it. Everything going so far? Everything okay?
Mm-hmm.
Good, James?
Yeah.
Any questions? James, any questions? You good?
No problem, yes.
Great. So here is our first of many CVTs today. I'm going to have to just copy and paste the link. Yep. And again, all you have to do, if you ever want to do this at home for whatever, just go to YouTube and type Boeing 777 CVT, and all the CVTs from Boeing are there. They're not from Boeing, they're from somebody else, but all of them are there. So if you ever want to refresh or something's still not good, then
Data Inertial Reference System provides flight data such as position, speed, altitude, and attitude. For the flight displays, flight management computers, flight controls, engine controls, and other systems requiring inertial or air data. The major components of the Air Data Inertial Reference System are Air Data Modules, the Air Data Inertial Reference Unit, or ADIRU, and the Secondary Attitude Air Data Reference Unit, or SARU. The ADIRU is the primary flight data source, while the SARU acts automatic ADIRU. The SARU is the dedicated data source for the standby attitude indicator. First, let's look at the air data part of the system. The air data modules are remote sensors which electronically supply pitot and static pressure information to the flight controls data bus. The air data modules receive and process data from 3 pitot probes and 6 static ports, 2 per module. 2 standby modules provide dedicated inputs to the standby airspeed indicator and standby altimeter. The ADIRU and SARU receive 3 independent bus inputs to calculate airspeed, Mach, altitude, and other air data parameters. Both units independently compare the inputs and validate which signals should be used in their calculations and other displays. The ADIRU and SARU also receive data from 2 angle of attack sensors and 1 total air temperature, or TAP probe. TAC is displayed on ICAS. Now let's examine the ADIRU in more detail. The ADIRU is a single fault-tolerant unit which replaces the inertial reference units found on some airplanes, or the mechanical gyros and inertial navigation systems on older technology airplanes. The ADIRU contains electronic sensors and non-mechanical laser gyroscopes, which measure airplane movement in all 3 axes. Signals from the sensors and gyros are used to calculate the airplane's attitude, heading, ground track, ground speed, and the airplane's latitude and longitude position. Before the ADIRU can calculate this information, it must accomplish a pre-flight alignment. Pre-flight alignment is the calculation of the airplane's relationship to true north and is done independently of any navigation aids. During alignment, the sensed gravity force is used to calculate the airplane's attitude, and the Earth's rotation force is used to determine the location of true north. The airplane must remain stationary during pre-flight alignment to properly sense Earth gravity and rotation. The process takes from 6 to 15 minutes, depending on latitude. Delay pushback or taxi until alignment is complete. To maintain navigational accuracy, a complete alignment is recommended if the time between alignments is expected to exceed 24 hours. Alignment begins with the ADIRU switch. The ADIRU switch is located here on the overhead panel. To realign the ADIRU, the switch must be left in the off position for 30 seconds and then pushed on to start a full alignment cycle. Primary electrical power is available. Position the ADIRU switch off and back on. Verify that the off light is extinguished. The ICAS memo message, ADIRU Align Mode, displays while the alignment is in progress. The only information the ADIRU needs from the flight crew is the airplane's present position. You will learn in another lesson how to use the FMS CDU to enter your present position. The crew enters the most accurate present position available. If global positioning system coordinates are available, they are the most accurate. The ADARU compares the enter position with the current GPS position or with the last known ADARU position and the sensed geographical latitude. The FMC also compares the enter position against the coordinates of the active flight plan's origin airport. When the alignment process is complete, the ADARU enters the navigate mode, and the ADARU align mode memo message is removed. Although the ADARU is very accurate, after entering navigate mode, errors accumulate. To compensate for this, the FMC calculates its own position using both ADARU position and other data. To provide navigational backup in case of dual FMC failure, the ADARU contains an identical magnetic variation table. Variation data for all locations between north and south 82 degrees latitude, except for some areas near the magnetic poles, is stored in both systems. The FMC is covered in detail in other lessons. System logic prevents the ADARU from being depowered if the ADARU switch is inadvertently turned off in flight. When the airplane is secured, positioning the ADARU switch off prevents discharging the main battery when AC power is removed. Position the ADARU switch to off. Verify that the switch shutter display is blank and the ADARU off light illuminates. If the ADARU switch is left on when power is removed from the airplane and the battery switch is off, the on battery light illuminates. And the ground crew call horn sounds. Before we discuss an ADARU failure, let's first look at its backup, the SARU. If data from the ADARU becomes invalid, the SARU automatically provides flight critical data to the same systems. The SARU provides speed, altitude, and attitude. The SARU, however, cannot perform inertial navigation functions. The FMC route map will be lost if GPS data is not available. The SARU can only provide a temporary heading reference, which is discussed next in non-normals. The ICAS caution message, nav ADARU inertial displays. If the ADARU is not capable of providing inertial navigation, attitude, heading, track, or ground speed data. On the ND, track and position data are provided by the GPS. Heading indications remain displayed for 3 minutes after the message appears. When the heading indications are removed after 3 minutes, the set heading line appears on the position initialization page of the CDU. On the PFD, air data and attitude indications are provided by the SARU. Flap maneuvering speeds cannot display. After 3 minutes, heading indications are removed, and most roll and pitch modes are no longer available. To regain the heading displays, the crew must enter a SARU reference heading in the set heading line. Enter a heading of 127 degrees. The entered heading remains displayed for only a few seconds. Heading information is restored. The entered heading must be periodically cross-checked against the magnetic compass and updated as necessary. Cancel the ICAS message. The CDU scratchpad message enter inertial position displays if the ADA-RU has completed its initial alignment process, but no position has been entered. The same message displays if the entered position fails the comparison check against either the GPS position or ADA-RU sensed latitude. The realignment initiated message displays if the same position which failed the ADA-RU latitude check is re-entered, or an internal problem is sensed during alignment, such as the airplane moving. The inertial origin disagree message displays if the entered position is more than 6 miles away from the location of the FMC active origin airport. Entering the correct position allows the ADA-RU to complete its alignment. This completes the instruction portion of the Air Data Inertial Reference System lesson.
Grammarly helps make your writing clear and concise, no matter where you are. Compose a cover letter.
Select the displays that show ADA-RU information after alignment. You've touched this before. Make another selection. You've touched this before. Make another selection. Seven displays can show ADA-RU information. Touch the highlighted area.
All right. So in a nutshell, we just went over the next 30 slides. I'm still going to go over them, but yeah, right? We have to align the ADA-RUs. It's, correct me if I'm wrong, James, the same way 747, right? Line it and then just put the last position and press set, right? So it's the same thing. It's the same exact way it's done. So aligning it shouldn't be hard. It does take forever though. That's the only thing I will say. All right, so standby attitude reference system, remember, it is a dedicated instrument that is used in the event that your ADA-RU completely fails, and it gets its information from the SARU and from the center pitot and static probe. So it shows the pilot's data, pitch, attitude, roll altitude, heading, indicated airspeed, and ILS, localizing glide slope deviation. All right, so if we look at it here, remember, center, think standby. So sending static ports, one on either side of the airplane, goes all the way over here to the static standby ADM. It should have just said standby ADM. But it's saying static because that's the static probe, pitot for the pitot probe, right? So standby ADM, and then that information is sent over here to the integrated standby flight display. All right? As simple as that. We have this new thing here called MMRs, or multi-mode receivers. We'll learn about that more later on in the day. But in essence, it gets ILS and glide slope information, as well as other stuff like GPS information. And so in order for it to know where it is, it gets those pieces of information from there too. Right? So left power supply assembly powers the static standby ADM and pitot standby ADM. Left PSA. And again, when you think standby, think center. So MMR sensor sends that data. All right. ARIN 429. That is the other main takeaway. Okay. I know everything and most things on the airplane speak 629. But the integrated standby flight display is an old system, or at least it's old insofar as it speaks on 429. All right? And this is just on the P2 panel. All right, that's what it looks like. We've all seen this before. All right, so what's going on here? Well, the integrated standby flight display, right? Left flight control DC, right? Or the left power supply assembly. And so what happens is that power, right, aside from the ISD, it also goes to the air data module power supply. And what it does is that since it's 28 volts DC, it splits it. It splits it half for the SADM, for the static air data, for the PIDO standby air data module, and the other half is for the static standby air data module, right? Where did I say that where the air data modules got their power from before?
Center PSA. Left PSA.
Right. So the left one got it from the left PSA, right one got it from the right PSA to the ADMs. Yes?
Left PSA power center standby.
Is this the picture? Yes. Nope. Not what I wanted to show you. No, that is. Yep.
That's a regular ADM.
Yeah, those are the regular ADMs. There you go. Right? We said left, right? Left PSA. Okay. Added to reference systems. All right. So again, aside from getting its information from the standby air data module, standby air data module from both the static and the PIDO. Look what else it's getting information from. The MMR. There's 3 MMRs we're going to learn, left, center, and right. The sensor MMR gives you localizer deviation and glide slope deviation, right? Your magnetic heading and ground speed, you're going to get it from the left Ames cabinet. And that's it. And then this is just telling you how to dim it. So if you want to dim the brightness of the ISFD, it's through the captain instrument panel lights dimmer. And that's it. And then this other thing is telling you that you could do a bite test of the ISFD through the CMCF function in the left and right Ames cabinet, which lives in the CPM COM. Okay? So again, the interfaces here, just letting you know that aside from static and air pressure, it also is going to get MMR deviation for localizer and glide slope. Because if that's your only source or interpretation, then you need to know how you line up with the runway, as well as your rate of descent, and then your inertial reference for magnetic heading comes from the left bus. Okay. This is what it looks like. It's really long. Cannon plug in the back, 2 static and a PIDO source tubes. And again, you just have different displays here. So you can have display brightness, indicated airspeed you see on the left side. You have your approach mode switch, barometric reference switch, roll attitude, light sensor, that's for the bezel, pitch attitude, altitude, standard select switch, barometric control, your heading. So in essence, it looks very much like your PFD. Right? That's because it is basically a backup PFD. And it has passive cooling, no forced air cooling. What are its functions? Again, you have to first look at what's going on here. So if you look here, one of it is to receive all this information, right? Hedostatic information, MMR, as well as the inertial reference. I think they made a mistake there, by the way, because it says MMR2. There's no such thing as MMR2. It's left, center, and right. So I don't know why they put 2. Doesn't make sense. But in any case, of course, it has a power supply because you have power to it. So here it is. It also has a bezel sensor, and so there's the lighting control depending on the sensor. If indeed it's going to automatically control it. You have your LCD display, your data control system processing, or the computer, basically, your graphics processing, so that if there is a fault, you send it to the graphic processor so that it can show it on the LCD. And remember, airing 429, 429, 429, 429. right? Here's a display of what are the possible pages, right? So I power up between the first 15 seconds. It's just going to say, it's going to pretty much be blank, and it's going to say init 90 seconds. Then on the next one, it's going to say the same thing, except that now you're going to have some indications. So if you notice here, as soon as you power up the plane, you're not going to get anything. You're just going to get these flags. Then all of a sudden, after 15 seconds, up until a minute and a half, you'll start getting your indicated airspeed and your altitude indication. And greater than 90 seconds, once it's fully booted up, you're going to get your entire display. All right? You can get a problem with the program pin error, so there could be an internal fault, or you can just have it completely out of order and it will stay out of order. Good thing though, it gives you the full code. That way you can look up on the fin what's actually going on.
There's no self-test for this one?
There is. That's right here. Hold up. It's coming up. I'll show you in a minute.
Okay.
There is a bite test though. Right? And so it's just showing you the attitude operation, how it looks like, if indeed. So here's your roll. Again, just in the same way PFD works. And then if you have a failure, you're going to get the attitude failure flag. And then this is a message you can have. It says wait attitude. It's waiting for the attitude, 10 seconds. If not, it's going to reset. If it doesn't get it within 10 seconds. All right, your altitude and altitude operation. So your airspeed on the left, your altitude on the right. Again, if it fails, you're going to get the respective flags, speed and altitude flags. They'll just be digital. Heading operation, same thing. Down on the bottom, you got a little compass. And if it fails, then you're going to have it blank. Approach operation, this is letting you know what's going on. If you are indeed approaching, and those are the messages, right? What mode you're in. Are you in approach mode? Back course mode? Any failure flags? So notice here, just like those very old localizer and glide slope instruments, you get the little orange flag. You get the same thing here, except that it'll be digital and it'll say localizer or glide slope. Okay? So all the different, and then here is what you were asking for. You have to press both the approach and the barometric reference. Press them both. When you press them both, you get into this bite test page. You go to test, functional test, hit it. If you need a return for whatever reason, you just press the reset and it comes back here. And if you want to get out of here, just press the reset mode and you go back here. All right, so 2 top buttons. That's all you got to do to get into a bite mode.
Let's take a look at the ISFD installed on both the ER and the LR Boeing 777 aircraft. You will notice that the top of the indicator has 2 select switches. You also have 2 select switches on the left side and one on the bottom, and a rotary knob on the bottom right-hand corner. When you make selections of the APP button, you can see how it brings up the multi-mode receiver indication for approach guidance to the flight crew on the display. The hectopascal, or inches of mercury, that select switch will change between those 2 values, and then by operating the large knob at the bottom right-hand corner of the display will change the value of your selection. At the top of that large knob is a select switch itself, and that would run it to standard day.
I think you meant to say sea level.
The 2 switches on the side allow for minute adjustments of the light intensity, but there is a fixed bezel